All right. Let me make sure that, yeah, I think it's working. So today, we're talking about harmonic functions. So still roughly speaking, following Gamelin. Of course, we're really following my guide to Gamelin, which is parallel yet different. And so from a purist perspective, in some sense, this section is out of order because it requires knowledge which we have not really derived yet. But the critical observation that we need really to kind of, which would maybe make an argument for this section being later, is that we can later prove that if a function is complex differentiable on a domain, right? So, if f is complex differentiable on a domain, in other words, f is holomorphic on D, what does that mean? D, which is a open and connected set, right? Subset of, complexes. And so say f is holomorphic on D means it's complex differentiable on an open connected set, right? Turns out, we don't have the technology to prove this just yet, but if f is holomorphic, it follows then that the derivative not only exists, but is actually continuous, all right? So complex differentiability on a domain necessarily implies continuity of the derivative on that domain, all right? Then, f prime is continuous on D, but actually it's even more than that. In fact, when you study this more deeply as we go on in this course, we'll find out that if f is holomorphic on a domain, the derivative not only is continuous, it itself is holomorphic. So, in fact, f prime is an element of the holomorphic functions on D. Right? And I think you can see where this is going. Then the second derivative of f is continuous and also, in fact, holomorphic, which is to say that if there's one complex derivative for a function on a domain, well, there's two, there's three, there's four. It's complex smooth, you could say. And all of those derivatives are continuous. Now, to prove that, we need some things from theory of integration on complex numbers. So this comes later. But I just want to say at the moment that the assumption of continuity is not a burdensome assumption. If we have a holomorphic function, continuity of the derivative is automatic. All right. Again, this is for a domain. We do have an example where there's an example, right, where, cautionary warning, there is an example where you have, so here, here's a picture of the complex plane, if you will. And so we have f, which is complex differentiable on x, on real and imaginary axis, all right? But nowhere else. So there is a function on the complex plane which is complex differentiable on the real and the imaginary axis. The example I'm thinking about is example 2.35. Since I'm talking about it, let me try to write it down if I can find it. Give me a second here. And the thing is, how do we prove it's complex differentiable? Well, that's easy. Now it's easy because the function I'm about to write the formula down for, all right, we can apply the Cauchy-Riemann equations. And so here's the formula. F of z equals to x cubed y squared plus I x squared y cubed, all right? So this is your u, this is your v, and you can show that ux equals to, let's see here, 3x squared y squared, which is vy, right? And, whoa. No. Oh, I'm sorry. I'm an idiot. Give me a second here. Vx is 2x y cubed, and actually, are these equal? And vy, or rather uy, is equal to 2x cubed y. Yeah, right. Now you're like, well, then the Cauchy-Riemann equations aren't true, right? Because we need what? We need ux equal to vy, and we need, yeah, vx is minus uy, or something like this, right? So this is the CR equations. And while the first one's true for this function, right? And by the way, is this function continuously differentiable? Yeah, the function's continuously differentiable on the complex plane because it's got polynomials for its coefficients, right? Polynomials are everywhere continuous. I mean, bivariate polynomials to be fussy, but notice that this is true. These hold for x equals to 0 and also for y equals to 0. Either one of those being true makes the Cauchy-Riemann equations true, right? Because the Vx and Uy are both 0, right? So they're equal to minus itself. But you see, that's it, right? Except for the coordinate axes, there's no place where the Cauchy-Riemann equations are satisfied, which means that the only place on the complex plane where this function is complex differentiable is, as I've drawn, the real axis, if you like, and the imaginary axis, right? Is there any place where this function is holomorphic? What does it mean to be holomorphic? Well, to be holomorphic means that you take a point, right? And you can find a little disk around it, right? And in that little disk around the point, the function's complex differentiable on that disk, right? No such point exists for this function. Every place you have complex differentiability, you try to draw a little disk around it, you got places off the coordinate axes where the Cauchy-Riemann equations fail, and thus it's not complex differentiable. So this cautionary example does not fit into this comment.
Are we saying that this allows us to move the function up and down?
What does the existence of the complex derivative on a disk allow? It allows certain constructions in terms of integral complex analysis, which allow us to prove the claim I'm making.
Yeah, essentially. So, how we add that constant because we're talking about families of functions. Are you saying that without that disk, we can't say that this is true for a particular family of functions?
Yeah, I just don't. I think if I was to look at the, we can calculate the, here, I can calculate the complex derivative, second, third, fourth, right? Yeah. It's pretty easy. Yeah. With respect to I'm only calculating it on the coordinate axes, right? So I'm not entirely sure this makes sense, but let me just, for the sake of answering your question, possibly. So f prime of z is what? It's partial f, partial z, right? Excuse me, partial f, partial x, rather. So we've got 3x squared, y squared. Now, my spider sense is tingling, mathematical spider sense is tingling. I feel like there may be something I'm about 90% sure what I'm saying is not hogwash. The reason I'm worried is that I built this tower of thinking over the assumption of continuous differentiability on a domain. Now I'm applying this thinking on lines, which may or may not make sense. I would have to think about it more, but just bear with me here and let me continue this possible hogwash. So,
Why aren't we doing partial z?
well, I want to show you something. So this is 6xy squared plus 2i y cubed, right? And f prime 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 of z would be 6y squared plus plus 6y squared, yeah? And so I don't believe the, at this point, you look at the, here we've got u, quote unquote, equal to 6y squared, right? V is equal to 0. So, uy is, okay, so like, fine. Right, so like, so the fourth derivative is 0. I'm not sure that the Cauchy-Riemann equations are still true, actually, on the, are they?
I didn't think they were true on the axis or a particular axis. Actually, yes, they are. But when you go with derivative, I'm not sure.
X equal to 0. I mean, x being 0 and y being 0, either x or y being 0 made both of these die, But, like here, all right, let me step back a second here. So this is, I'm trying to think about the Cauchy-Riemann equations for this. Are they still true on the coordinate axes?
Yeah.
See, because this would be my u, this would be my v, right? So ux is 6y squared, and vy is 6y squared, right? Okay, so those are equal. Great. Uy is 12xy, and vx is 0. Okay, so yeah, uy is still equal to minus vx, provided either x or y is 0. All right, never mind. It's not. I was hoping to see some kind of like maybe departure from the Cauchy-Riemann equations as I looked at the higher derivatives here, but it doesn't happen. I was just wishful thinking on my part, but it didn't work out. But the fact remains that this function is nowhere holomorphic. And so, anyway. All right, so enough about this. me stop chasing this rabbit and ruining this lecture. I mean, this is not bad. This is a discussion we should have, actually. But, all right, so what is a harmonic? So the key theorem that we're using from advanced calculus today is that for twice continuously differentiable functions, we have that partial x, partial y, f is partial y, partial x, f, right? So we can commute the order of partial differentiation. So we're going to be looking at complex functions which are holomorphic, all right, and therefore they have continuous second derivatives. So we can apply this to such holomorphic functions, all right. All right. So in Rn, and there's various sign conventions here, but some people use this sign convention, some people don't. Triangle is like partial squared, partial x1 squared, partial x2 squared, partial xn squared. So if you take triangle on a function of x1 through xn, it's like, we could write it this way: partial squared x1 u plus partial squared x2u, partial squared xnu, or in 3 dimensions, this would be partial squared u, partial x squared, partial squared u, partial y squared, partial squared u, partial z squared, or we could use the notation like uxx plus uyy plus uzz, all right? This is called the Laplacian of u. Well, anyway, this is the Laplace operator, this triangle thing, all right? And so you can study solutions of the Laplace equation. The Laplace equation is just set delta u, I guess triangle u equal to 0 here, all right? That would give you Laplace's equation, right? So if I set this equal to 0, we're looking at Laplace's equation in R3, all right? So you can look at Laplace's equation in all kinds of different contexts. You can look at it on curved spaces. You can look at it in the plane, and a lot of the famous problems of mathematical physics involve, like this Laplace operator. And then sometimes also like a time derivative, like the heat equation is involving like the Laplace operator and a time derivative. And the Laplace operator also appears in Schrodinger's equation when you study quantum mechanics in 3 dimensions. So this is an important operator of mathematical physics. Now for this course, we're in complex, right? So for us, here's our definition. And by the way, solutions to Laplace's equation are called harmonic functions, all right, generally. But here for us, our current context definition, all right, so uxx plus uyy equals to 0 is Laplace's equation. So this is what we mean by Laplace's equation. Of course, in the complex plane, right? And solutions to Laplace's equation are called harmonic functions. All right? So, what can I tell you? If I can find a working marker here. Oh my goodness. That rabbit ran for a while. Let's see here. So, theorem. If f equals to u plus iv is holomorphic on a domain, right? Then u and v are harmonic on D. And let it be understood that D is going to be a domain, all right? An open connected set. What do I mean by harmonic on D? I mean they solve Laplace's equations on that domain, all right? That's what that means. So here's the proof. So we assume, good grief, we assume u and v twice continuously differentiable on D, and that comes again from the later theory. My apologies. Note, we have what? We've got ux equals to vy, and uy equal to minus vx, since f equal to u plus iv satisfies CR equations, right? It's holomorphic. consider then partial x, partial x of u, right? Plus partial y of u. All right, so let me rewrite that a little bit. This is partial x of ux, right? Plus partial y of uy. Let's see here. So just, all right, now we have what? We've got ux is equal to vy, right? So this gives us partial x of vy by the Cautionary-Riemann equation, right? And then partial y of what? uy is equal to minus vx, isn't it? Again, by the Cautionary-Riemann equation. And just unpacking the notation again, this is really what? I'm going to use the shortened notation. This is partial x, partial y of v, minus partial y, partial x of v. I pulled the minus out, right? There's three competing notations for partial differentiation, right? The sub x notation, the full-blown partial x notation, and also this abbreviated. I like this notation. It's got the best of both worlds. But anyway, by theorem, sometimes called Clairaut's theorem, you know, that we can flip derivatives for twice continuously differential functions, we got that that's zero. In other words, holomorphic functions have harmonic component functions. It's pretty neat, right? So, example 1, we have f of z. I use e to the z as a starting example. So that's e to the x plus iy, which is e to the x, e to the iy, which, by the way, is e to the x cosine y, plus I e to the x sine y. So the theorem above says that u equal to e to the x cosine y and v equal to e to the x sine y solve, you know, phi xx plus phi yy equals to 0, right? I can put phi equals to u, it solves it. I could put phi equal to v, it solves it. And it's easy enough to see why, right? Because when you take the twice, yeah, and exactly, you get back with a minus from the y derivatives, and you just get the thing back again from the x derivatives. So, definition. If u is a harmonic function on a domain D, domain D, all right, and u plus iv is holomorphic on D, all right, then we say v is a harmonic conjugate of u. Of u on D. I say a harmonic conjugate because, you know, there are, like, many choices. Okay, like, well, just a, you know, let's see here how to say it. So if, you know, if you have u plus iv, you know, holomorphic, then u plus v plus any constant, let's say v naught, is likewise holomorphic on D, right? Because if we add a constant, and redefine the v, it's still going to satisfy the Cauchy-Riemann equations because the partial derivative in the Cauchy-Riemann equation kills the constant v naught, and so there's, lots of choices here. So, this is a very popular introductory exercise in complex analysis. Let's work through one. So consider u equal to, let's see here, I guess I could follow the notes. Sure, why not? X squared minus y squared, right? We'll use the domain as all of the complex numbers themselves are a domain, right? Is that harmonic? Is this a harmonic function? Well, we can check that pretty quick, right? So, note uxx plus uyy is equal to 2 minus 2, which is 0. So, u holomorphic. So we're good on that, right? Now we want to find the goal is to find the harmonic conjugate of u. All right. And I'm going to do it the low-tech calculus 3 way here to start with. So what we're really trying to do is we're trying to solve the CR equations. And what are those? Well, that's, ux is equal to vy, and uy is equal to minus vx, right? Which is what? Partial v partial y is equal to 2x. And we're trying to solve partial v partial x equal to minus partial u partial y, which is, by the way, 2y, right? Bernoulli's equation.
Like partial f over x equal to partial big D, partial big F over 1 and partial big F of the other one.
Mm-hmm. But Bernoulli's equation is...
Exact equation.
Oh, exact. This is like the exact equation calculation, sure. But yeah, that's the right thing to think about, or finding a potential for a conservative vector field. But the point is, integrate. So if we integrate the first one with respect to x, what's this tell us? This tells us that v, right, is equal to what? 2xy. Integrate this with respect to y. 2xy plus some function of what? Possibly a function of x, right? And then if we plug that into the second one, we've got partial v partial x is equal to what? Partial x of 2xy plus h1, which is what? That's 2y plus partial h1 partial x, right? Well, that has to be equal to 2y, which is not a problem, right? The 2y's cancel, and this tells us that we just face the problem partial h1 partial x equals to 0, which tells us that h1 is a constant, right? So lo and behold, we found the harmonic conjugate v is equal to 2xy plus some constant. And that is what all possible harmonic conjugates to this given u look like, right? So there we go. We found the harmonic conjugate, plural, all right? Now, let's do a little bit more. If we take c equals to 0, and that's just a choice, right? Then v is equal to 2xy. And if you look at u plus iv, what do we got? We've got x squared minus y squared plus 2ixy. And if you tilt your head and squint and look at that, yeah, that is a quadratic. It's really just x plus iy squared. Which is to say that u and v are the component functions of complex function f of z equals to z squared. So when we're faced with the problem of finding a harmonic conjugate, there's a couple different ways we could go. The one way we could go is like I just did in example 2, just to integrate the Cauchy-Riemann equations for the given harmonic function, right? But there's a more fun way to go, which is to try to identify which complex function takes the given harmonic function as a component function. So let me illustrate that in example 3 here. Like, suppose you have, u equals to, I don't know, natural log of the square root of x squared plus y squared. Ooh, I'm not sure that's holomorphic. Well, curses. I'm sorry, I'm a little bit befuddled at the moment because I have proved over here that holomorphic functions are necessarily harmonic, right? And yet what I was thinking about was the log, capital log, log of z is, what is it? It's the natural log of the modulus of z, right? Plus I arg z. So I thought that would, this is true on the slit complex plane, right? On the slit complex plane, that's holomorphic function. So, but I'm just computationally, I'm having trouble with it. Like if u is equal to, this is 1/2 the natural log of x squared plus y squared, if you like. And of course the other one is v is, let's just take it in quadrants 1 and 4 just to be simple. Inverse tangent of y over x, right? So I'm having trouble seeing that uxx plus uyy is 0. Why am I missing it? I'm very, I have, sorry, Audric, I'm at a loss here. There's something I'm missing. Oh, I think it's the second derivative. So the first derivative, I'm not actually, I keep thinking first derivatives in my head are second derivatives, and they're not, right? So the first derivative gives you x over x squared plus y squared, right? Yeah. Plus partial y over x squared plus y squared. Aha. And then when you do the quotient rule on those, you get x squared plus y squared minus x times 2x, right? And then on the other one, you get x squared plus y squared minus y times 2y. All of that over x squared plus y squared squared. Oh, phew, what a relief. I was like, how can that be true in general but not true in my example? Because I actually need to do the calculation and not just rely on thinking. So that gives me 2x squared minus 2x squared, 2y squared minus 2y squared. And so that's 0 for, that's actually 0 for, well, it's for c minus, I guess I should say. I mean, okay, so that's a harmonic function, right? So what I was, now I've ruined my example, right? But ruined my example. Because what I was going to ask you was, u equals to the natural log of the square root of x squared plus y squared. Find the harmonic conjugate to that. Well, light bulb thought appears. V is equal to I arg of, x plus iy is going to be the harmonic conjugate of that, because this plus, not without the I, log of the square root of x squared plus y squared plus I times the argument of x plus iy, that is the logarithm, which we know is holomorphic. And then by the theorem that we proved, it follows that v is a harmonic conjugate, right? So if you can pair a given harmonic function with another function that together they give you a function which you already know is complex differentiable, well, hooray, You've done it. See if I can try another one here. Let's see here. How about this one? Can we find a harmonic conjugate for this guy? So sine x times cos y, right? So let me tell you, I'm like, wait a minute, I've seen this before, right? When we were messing with sine z, what was that? Sine of x plus iy, right? Which is sine x cosine iy plus cosine x sine of iy, right? And what was the relation between cosh and sinh and sine and cosine? Remember?
Yeah, it was a former problem. You get a cosh is equal to cosine I x, right?
Yeah. Well, or we could do it this way. Cosine of iy is cosh y, right?
Yeah.
But then sine of iy, I'll write it out because I'm never sure about this. 1 over 2i e to the iiy minus e to the minus iiy, which of course gives you what? 1 over 2i e to the minus y minus e to the y, right? Which gives us I times 1/2 e to the y minus e to the minus y. In other words, yeah, I sinh y, which we've derived before, but there we derived it again. So what we got is sine z is sine x cosh y plus I times cosine x sinh y. So with this knowledge in hand, we go, thus, v equals to cosine x sinh y is harmonic conjugate. conjugate of u. So anyway, I wanted to share that trick with you guys. It's not in my notes exactly, but it's one I often find useful for these kinds of questions, all right? So that brings us to the next section. I mean, there's one theorem at the end of this, which is, I'll read it. Let D be an open disk or an open rectangle with sides parallel to the axis, and let U be a harmonic function on D. Then there exists a harmonic function V on D such that U plus IV is holomorphic on D. And the harmonic conjugate V is unique up to adding a constant. So that theorem assures us that there exists a harmonic conjugate. And it also says that for every harmonic function, every real harmonic function, there exists a corresponding complex differentiable function on that domain, which takes it as its real part. So there's obviously an important connection between complex differentiable or holomorphic functions and harmonic functions, right? These are fellow travelers in the mathematical world, if you will. Now, so the next section is on conformal mappings, all right? So I want to start talking about that today, conformal mappings. And so here's the basic picture. What do we mean by a mapping on the plane being conformal? So if you've got the z-plane, right? And then over here you've got the w-plane, all right? And you've got a curve, all right, let's say like this. And you've got another, so I'll call this gamma 1. And over here, you've got the image of it, F composed of gamma 1, right? And then you've also got gamma 2. And then over here, you've got F composed with gamma 2, all right? And F is mapping from here to here, right? W equals to F of Z is the way we do it. Then F as a mapping from the complex plane to the complex plane is said to be conformal if it maintains the angle between the angle of intersection between curves. So like this and that, this angle here, and over here, this and that, same angle. That's conformality. What it means to be conformal is it maintains the angle between curves as you map them.
Yeah, I mean, like, I can see that, like, with R2 C, but R C.
Yeah.
But it's like,
So the key calculation, and so suppose F is holomorphic. Suppose F is complex differentiable, and gamma 1, gamma 2 are subsets of that domain, all right? Then you have the chain rule. d dt of F of gamma of t is df dz of gamma of t times d gamma dt. And so what is the derivative? You can write the derivative at gamma of, so let's, set t equals to 0 at the point of intersection just for convenience, yeah? So let's let P be the point of intersection. All right? And we'll assume P equals to gamma 1 of 0 equal to gamma 2 of 0. We'll parameterize our paths such that they both go through the point at time 0. We can do that. And so then, f prime of p, right? F prime of p we can write in polar form, right? It's what? It's like r, like r e to the I alpha, let's say, yeah? So check it out. F composed with gamma 1 prime of 0 and F composed with gamma 2 prime of 0. What are they? By the chain rule, right? They're exactly r e to the I alpha, right? Because that's the derivative at 0, this thing. And then gamma 1 prime of 0.
So how do you take the prime of both at the same time?
Gamma 1 prime of 0. Gamma 2 prime of 0. What's that? So I did the identity for gamma, but we can specialize this to gamma 1 or gamma 2.
Yeah.
Then evaluate this at t equals to 0. And use this notation for f prime of p, which is, by the way, f prime of gamma 1 of 0.
Okay.
Yeah, that
I didn't use the same notation as you, that's why.
that's fine. It's fine.
I just wrote it out like F, like actually composed.
Sure.
And it's like where we can gamma 1.
It's all good. It's all good. So, the green vector right here, this was gamma 1 prime of 0, right? This guy over here was gamma 2 prime of 0, right? And so if I need to come up with a name. I'm going to call this V1. I'm going to call this V2, okay? Just for the sake of, so here's your V1, here's your V2, the transported ones. How are they related? What's
Orthogonal? Or, no, I guess you can say that they're, if we preserve that angle between each other.
Yeah, why do they preserve the angle? Because what's going on here, this formula, what does it do? It multiplies, like, so V1 and V2, how are they related to gamma 1 prime of 0 and gamma 2 prime of 0? Exactly, exactly. We're taking the original vector, the original tangent vector, gamma prime of 0. We're stretching it out. We're dilating it by r. Or compressing it, depending on how far is less than or greater than 1. Same for both, right? And then we're rotating it by angle alpha. So whatever the angle was before, as this map goes over here, it just rotates it by alpha,
Yeah.
whatever that is.
But you didn't define F prime like that?
Well, every complex number has a polar representation.
Yeah.
So,
Okay, and then you can always just pull it out and
yeah.
evaluate at 0 whatever
Right.
point you choose.
Now in the notes I formally calculate this. I calculate the dot product. I compare the dot product of these two vectors to the dot product of those two vectors and show that the angle that they define is equal. Gives you the same cosine and hence the same angle. But geometrically, the argument is just that the derivative is rotating all vectors at that point under the map, right? The derivative is rotating all vectors at that point by the same phase factor, e to the I alpha. So it maintains angles between curves of intersection. In other words, this argument I just gave you proves that a holomorphic mapping is necessarily conformal. Holomorphic implies conformal. The converse is not exactly true. You actually have to add the assumption that it's conformal and orientation preserving. So orientation has to do with, right-handedness. It has to do with maintaining. So like in a disoriented mapping, you could have, like V1, you could have like V1, this first one rotating in the counterclockwise sense to the other one, right? In a disoriented map, that's not really the word, but
Are you saying like both of them could be rotating different directions?
you could have like this before, right? then after the map, you could have like this. So maybe the angle is the same, but
Yeah.
that one's counterclockwise, and then after the map, it's clockwise. That kind of thing can happen with a mapping which is not oriented. The conjugate map is a good example of that. The complex conjugate map is disorienting because it flips things over the, well, anyway. So that's what we're talking about next time. And the really cool thing, of course, is that this also, especially interesting as it applies to orthogonal curves, right? Curves which meet a right angle. This says that if you map curves which meet a right angle under a holomorphic map, well, they automatically may map to their image curves are likewise at right angles. And then the other really cool thing is if we look at level curves of U and V, they have to be perpendicular because the Cauchy-Riemann equations are going to tell us that the level curves of the harmonic conjugates, level curves of harmonic conjugates are orthogonal trajectories.
So this is only for holomorphic maps, right?
Yeah. Well, some of these things can be said for anti-holomorphic maps, but
So holomorphic always implies conformal.
yeah, this argument right here shows you holomorphic implies conformal. I wanted to get that under our belt so we can focus on the examples next time. So, thank you.